Yeah, so I'm here to talk a little bit about what we do. What we do is in the context of a project. That's one of these EuroHPC Centers of Excellence. So it's kind of another part of the EuroHPC ecosystem that turns out I'm the only one here representing that at the moment. But so I'll give you a little taste of what we do. But each of the Centers of Excellence, they're kind of domain specific. So ours is called MultiXscale, and it's about doing simulations of things across different scales and coupling those together. Later on, what I'll specifically talk about is a service that we provide. It's called EESSI, and it effectively looks like streaming scientific software. So I want to give you a brief motivation for why we're doing this, or why we see this Center of Excellence as a useful platform to show this. Slides are not great, don't know why. So MultiXscale, it's a collaboration between a scientific network that exists for, I think it's more than 55 years at the moment. It has its headquarters in Switzerland, but it has a nodal structure. So there's nodes all across Europe. That's called CCAM. There's three pilot use cases that come from the CCAM network. And then we have the technical partners. The technical partners are the people who are connected to the EESSI project. And we provide the tools to allow the application software to be available on any platform. So the targets in MultiXscale are about increasing the productivity of the scientists who develop, it's improved, I think, yeah, who develop or use open source codes, the performance of these codes on the hardware that the scientists have access to. So in particular, we're talking about the EuroHPC ecosystem, so that's that hardware. But we also want the portability of the codes in the workflow. So we want to be able for people to use this software all the way from their own laptop to a server, to the cloud, and to these HPC resources that they have access to. So the particular focus of MultiXscale is this multi-scale modeling and leveraging then the resources that we can get within EuroHPC. And the idea is to encourage, push even the community towards using these exascale resources, because they are plentiful and they are useful, but they are sometimes hard to use. So the first use case I wanted to just mention is batteries, in particular talking about supercapacitors. Supercapacitors are like the sprinters of the battery world, and they can absorb and release a lot of energy very, very quickly. So they're already being used in supercars, so in very expensive automobiles. But they're really interesting for other applications like regenerative braking, in the case of like trains and buses, and so heavy transport and big large vehicles, heavy vehicles. Predicting the properties of the materials that you use within these supercapacitors requires a lot of performance, and you need to do this at very, very large scales as well. The second use case is ultrasound. So what we want to do is kind of create a digital twin for the ultrasound process. So probably a lot of you know that ultrasound is used for diagnostic purposes, but it's actually used in quite a crude way. So part of this process is to try and improve the protocols to effectively, ideally you simulate while you're using the product, and then it's effectively like creating an autofocus capability for the ultrasound process. This is also interesting, not just because ultrasound is used for diagnostics, but it's also used for treatment as well. So it's non-invasive treatment as well, so it's interesting for that purpose. The last one, our pilot use case is helicopters for civil applications. So helicopters in general, to simulate them, it's a complex process. You've got fluid flows around the helicopter body itself. You've got a complicated structure that's rotating. You need to couple these together, these different things. And then that typically comes, if you want to do that in high detail, that's restricted by the high computational cost, but you need high fidelity. So it's just a complicated thing. And we all know that if we want to land our helicopter on the back of our yacht, this is an important issue for us. Scientific motivation around so we have these scientific motivation, right? These three pilot use cases, and then so the EESSI project comes with like technical innovations to help the scientists do these things. So each of the pilots is dealing with phenomena that manifest at multiple scales, and they typically use many different methods at the same time, and a variety of different software applications. So it's not a single software package that does everything that they need. They're typically cherry-picking from different cases because they want to integrate different approaches into their flow, and they want to couple these together, right? So the coupling is the hard part of what they do, and then this coupling is typically unique to the situation that they have to deal with. But then they also need to be able to do this at scale, right? To take advantage of the resources that they have access to. And you know, in Europe, the largest resources that we can have access to for free are within EuroHPC. But having access to the resources is not enough. We need to get the scientific workflows, their actual entire workflow from beginning to end, onto these systems and make it as easy as possible for them to use them. So finally getting to what we do on the technical side. So what is EESSI in a nutshell? It stands for the European Environment for Scientific Software Installations. It's a shared repository of scientific software installations. Not a recipe about how to build software, but the actual software itself. So you can take it and you can run it straight away. It avoids a lot of the duplicate work that you see across all the HPC sites, because we collaborate on the same shared software stack. It gives you a uniform way of providing the software to users, regardless of the system that they use. And that means that it will work across laptops, it will work on your personal workstation, HPC clusters, the cloud, all of those. And we have support for lots of different CPUs. We have support for interconnects, so we care about the scalability of the software. We also have support for GPUs. And our focus is really on performance, right? So we want to do this with no cost in terms of performance, right? So this is something, we've talked a little about containers, but you do typically see with containers that you see a cost, right? Because with a container, to make it portable, you have to make it generic. To make it generic, it costs you in terms of performance. So we're trying to avoid that. So the general architecture looks like this. So basically, we have, on the bottom here, we have the host operating system, right? So that's Linux. And then you have kind of emulators that you can use within WSL for Windows, and then Mac OS as well. You can also use that there. And then we still see all of the hardware that you have. So we see your interconnect, we see your GPU drivers, we see your resource manager, Slurm. They're all on the host operating system. What we do is we provide a file system layer, so a way to distribute what our software stack. On top of that, then, we built a compatibility layer. So that's what gives us independence from the underlying operating system. And then on top of that is the one where we care about the performance, right? The software layer, the scientific software. So we build optimized applications and all their dependencies for the specific CPU architectures that you're using at the time. And this is done with lots of different open source software, right? So we've got CERN VMFS, which comes out of the CERN experiments. It's around for a long time. They've used it for a long time to distribute software. We've got Gen 2, which is what we use to create and the compatibility layer. You can kind of think of the compatibility layer like a container, but it doesn't require a container runtime. So it means you can still directly see your hardware. You can still see all the user space. You can see everything inside. You don't need to perform any tricks to do that. It doesn't need a runtime. And then on top of that, then we build our software with Easy Build. And the user interface is something called LMOD, so the module environment. If you've used an HPC system, you may have heard that before. And then we test everything, right? So for testing, we use lots and lots of CI processes, but we also have reframe as well. So we don't want to just test the software. And when we install it, we also want to test its performance and its scalability. The idea being that we can do that directly on the EuroHPC resources. And we support a lot of architectures. So we already support Intel, AMD, and ARM. And we're also working on RISC-V support. So we've done some initial work on that as well. What does it effectively look like? And basically, the experience is like streaming scientific software. So it doesn't really matter where you land. You just use the same commands that you used on the other system. You load the software. It automatically selects the right architecture for the system that you've landed on, and you can start running straight away. So you don't have to install anything. What's the status right now? So we have a production repository already available. Right now, that has about, I think it's 320 applications inside and thousands of extensions. Everything we do is open source, right? So we have Ansible playbooks for all of our supporting infrastructure, our scripts and our documentation. That's all within an organization on GitHub. So if you wanted to look around, you could. We provide infrastructure, so we have to to actually deliver the software, we need to have an infrastructure that supports it. That's through CERN VMFS. So the main copy of everything we do is in the University of Groningen. And then we have two strata. We have actually more than two, but we have two ones that you would use as a user. One is in Azure and one is in AWS for all of the software that we provide. Our software right now, in terms of the CPU-only side, is things like that are common in the scientific space. So things like Bioconductor, GROMACS, OpenFOAM, or TensorFlow. PyTorch is also in there as well. In terms of our hardware targets, the biggest ones would be ARM and x86. So we have generic support, which means it will run everywhere. But then we have specific support for particular instruction sets. So that's Haswell and Skylake, so AVX 512, vector instructions effectively. Zen 2, Zen 3, we're also working on Zen 4 now. And then in the ARM space, we have Neoverse N1 and Neoverse V1 as well. So these are all very relevant to the Euro HPC architectures. We have working NVIDIA GPU support, but we're currently figuring out how to exactly manage that. And we're currently adding additional applications in the GPU space. And we get support, right, from the cloud providers. So we get significant support from Azure and AWS, lots of sponsored credits, which allows us to provide the architecture that we do, the infrastructure that we do. And then just finally, just some links, lots and lots of links. I hope you get a copy of the slides so you could follow those. And then some things that I have to show because it's a funded project, right? So there we go.